Okay, 2.3, discontinuity and continuity are really an important discussion, and really it's a lot of the kind of genesis of why calculus even started, dealing with these jumps in graphs. And continuity, just like always, the definition is more confusing than the concept. Anything in math defined, because you don't get to see it in a definition. It says a function is continuous at an interior point C. They always use C for whatever reason. Now, in this case, C is between A and B, but it doesn't have to be right between. It could be anywhere along here. If at any point C, take a look, C, my limit at C is this, and that's also f of C. Well, wouldn't that always be the case? Not if I have a hole. The limit is here, but f of is not here. It doesn't exist. This should be called, here's what they should say. A function f of x is continuous at an interior point C if you can draw the function without lifting up your pencil. That's what it should say. It's continuous. Well, holy cow, that makes sense. In fact, that's what I would think it would be. I would think that that's not continuous. I would think that's not continuous. I think that's continuous. Don't lift up your pencil, continuous. That's what they're saying up here. Okay. F of x is continuous at a left endpoint A, or continuous at a left endpoint B of its domain, if f of A from the right is, so we would actually say this is continuous, but we would only talk about it from the right. That makes sense too, doesn't it? I mean, it ends, it stops, we don't start doing anything over here, but primarily we're going to be dealing with the ones in the middle, so if you lift up your pen, it's not continuous. That's pretty easy. All right, discontinuities. We're going to have to be comfortable with these. I think 3 of these are absolutely obvious, and the oscillating one may be a little bit more confusing. So, a discontinuity is a place on the graph where the continuity doesn't exist. You don't say. Pretty clear. One type is called removable. Discontinuities are removable if we're able to evaluate limits at that point. Well, when can we evaluate limits? Only when we're in left and right hand agreement. Well, if I'm in left and right hand agreement and it's discontinuous, what do we have there? We have a hole in the graph, don't we? A discontinuity is called removable. Oops, I'm going to bring this down and let it touch. Sorry, it should be touching. So we're in agreement here that we should be at that point. Well, that's not very good. I'm going to redo that. We're in agreement there, but it's discontinuity. That is called removable. Well, that's a pretty darn good name for it. I removed a point. So that is removable discontinuity. Here is another removable discontinuity that's a little bit different. I can remove it and put it anywhere above or below there, and that's still called removable. This is the one that might get people, because if you look at the next type of discontinuity, it's kind of like, isn't that a jump? It's not a jump. That's still removable discontinuity. A hole is synonymous with removable discontinuity. Right? Jump discontinuity occurs when one-sided limits from the left and right do not agree. Here's jump. Oh, that makes sense. Do those limits exist? No. In fact, it says so in the definition of a jump. It jumps and starts somewhere else. This one doesn't really jump and start somewhere else. It's just removed and placed somewhere else, and we just continue down from here. Okay? Infinite. Approaching infinity from the left, approaching infinity from the right. So if this was -3, this is discontinuous at -3. Even though the hands from left and right are trending both toward infinity. Now, we would say the limit of this from the right side is infinity. The limit from the left side is infinity, but the limit at -3 does not exist. We could talk about infinity from left hand, right hand, but not for just the plain old limits. That's what I'm saying. Easy, easy, easy. It's just learning the language and how to communicate it. That could also be clearly the limit doesn't exist here, but left hand limit is infinity, right hand limit -infinity. Asymptotes. Then oscillating. I'd like you to go ahead and let's graph this in our calculator, and let's go from, for right now, x min, let's go -1 to x max 1, and let's zoom fit that guy. And I'll get caught up with you. If you're playing along at home and you got your calculator, try that. Zoom fit is zoom 0. Let's get focused here. Now let's take a look. Is that the right graph? That looks startlingly wrong. Yeah, that is not the right graph. Let's try that again. We've got sine of 1 divided by x. I didn't zoom fit. Zoom 0. Pretty boring and then pretty spastic. So, if I'm interested in what's going on around 0, which seems like that's the interesting point, I'm going to go back into window, and I'm going to go -0.001 to 0.001. And we're going to really zoom in and see what's happening, because it looks nuts at 0. So I graph this guy. And I need you to understand the graph is not, and look how it kind of just steps right over x equals 0. See that gap in there? It's having problems with x equals 0 as it should. But I do need you to understand that I often say our TIs, they do not graph by going, they go tick, 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 and connect the dots. These things would be, these peaks and valleys would be filling up this curve from -1 to 1. What's happening here? Zoom back in here. What's happening as x approaches 0, let's say x is 0.1, we're taking the sign of 10, and x is 0.0000001, we're taking the sign of 1,000,000. As we approach 0, we're just running through the periods faster and faster and faster and faster and faster, until we're trying to fit infinity periods in, right? So this is called oscillating discontinuity. And this is kind of a sneaky one. The oscillation has to occur between two fixed points, in this case -1 and 1, and it has to go faster and faster and faster and faster, indescribably fast as we get to it. So, as mentioned before, I believe in this class, let's say we have some decreasing sine function, and we got sine starts out like this, and then it gets shorter each time. Pretty soon it's just barely wiggling right over there. That would be a sandwich theorem type problem that we could say, no, the limit's 0 eventually at infinity, even though it's oscillating faster and faster and faster and faster and faster. Okay? All right, intermediate value theorem. Here's another one. I'm going to try to make it sound complicated. Wow, is this a simple concept, but a really important one in calculus. A function y equals f of x, the height at x, that is continuous on a closed curve. What does continuous really mean? We don't pick up our pencil, right? So I've got to get from here to there. From A to B, I've got to get from here to that point. It's continuous on A to B, takes on every value, the height, from the height of A to the height of B. If I start at A and I get up here to B, and I don't lift my pencil, I got to hit everything from here up to there. I didn't necessarily have to waste time down there, but I can come down here and wiggle around all I want. Eventually, I'm going to have to hit all of the values between there. When we see it that way, it's kind of like, well, no kidding. If it's continuous, I can wait. I can mess around, but eventually, I got to run through this no man's land, right? Every step of the way. That's all that says. But simple as it sounds, we'll use that in some complicated problems later on. Find the points of continuity and the points of discontinuity. Well, it's kind of silly, because if we find continuity, by default, we found discontinuity, or vice versa. The easier ones to find are the points of discontinuity. This is x plus 1 on factored x minus 3 times x minus 1. This graph has issues. Is there a hole in this graph? If this was x plus 1 down here, there would be a hole at negative 1. If there was an x minus 3 up here, there would be a hole at 3. There are no holes. However, because x cannot equal 3 and x cannot equal 1, and they aren't holes, we know for sure in rational functions that they are locations of, you can say it, asymptotes. So the graph of this, we might not have to graph it to do this, has an asymptote at 3 and an asymptote at 1. Would we have any other points of discontinuity? Do we know already what kind of discontinuity we have? What's going to happen? It's either going to go up here or down here. It's either going to go down here or up here. It's either going to go up here or down there. It's either going to go up here or down there. We have infinite discontinuity at x equals 1 and 3. So where is our continuity? That's actually harder. Everywhere else. We have continuity at all values, or all real numbers, you could say, except x equals 1 and 3. It's almost kind of like, duh. Okay? All right. Take a minute, see if you can come up with the cotangent graph. Try to do it without looking up. If you need to be looking up, I'm going to be building it here.
I'll do the weight, Jeff.
You too, Shane. Maybe we don't remember what cotangent looks like. If we don't remember or memorize what the graph of cotangent looks like, we are certainly not out of luck. We are out of luck if we don't know what cotangent is in terms of x, y's, and r's, or at least SOHCAHTOA it. X's, y's, and r's, what is cotangent? It's x on y. It's adjacent on opposite, right? Tangent, TOA, opposite adjacent. So this is adjacent x on, so if I built it like this, it would be x on y. Okay, so at 0, cotangent x on y is 1 on 0. 1 on 0 undefined. That's helpful. That's exactly the kind of thing we're looking for. The next nice, really, really convenient value right here, at pi on 2. Tangent x on y, 0 on 1, it's 0. The next really convenient value, pi. At pi, x on y, negative 1 on 0, undefined. At 3/2 pi, x on y, back to 0. Along the way, I shouldn't have put that one in yet. At this point right here, this is a 45, so this could be 1 to 1, 1 on 1, 1. So we're 1. And now once we got that, it's like, oh yeah, I remember. We ought to have it from there. Okay. So our points of discontinuity, we got a bunch of them. Question there?
How do you know that it goes down like that instead of going the other way?
Okay, here's pi on 4. At pi on 4, I'd be right here, correct? X on y would be positive on positive. So it's got to be positive. Is that all right? Okay. So my points of discontinuity are at 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi and 0 pi and negative 1 pi. Any integer value of pi, right? So we have discontinuity at x equals multiples of pi. N is an integer. What kind of discontinuity? Pretty easy, isn't it? Infinite. Now, it's really tempting to say jump. And really, infinite discontinuity is really a jump. But because it happens so often, it has its own special name. Pretty easy. So where is the graph continuous? Well, it is continuous all real numbers except x equals n pi. Because it was discontinuous at n pi, so everywhere else. I mean, you almost want to just put that C above, everywhere else. Okay. Any questions there? Okay, just to clean this up, the graph didn't print out very well. This is a circle, and I know that because if I look up here, 0, this is a factory that doesn't handle 0. We see it right here. This is a factory that does handle, so this must be a circle as well. It does handle 1, this is a circle, and 2. It does not handle 2. It handles less than 2 and it handles greater than 2, but it doesn't handle 2 and it doesn't handle 3. So we've got that. We good there? Careful, make sure you're answering the question being asked, because sometimes they ask just for f and sometimes they ask for the limit of. Does f of 1 exist? If so, show me what f of 1 is. Fingers. Yes, 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 yes. Let the record show that most people are saying that f of 1 is 1. It is. That's f of 1. So yes, it exists, and I'm going to put f of 1 equals 1. I think we should probably be specific why. Does the limit as x approaches 1 of f of x exist? Does the limit exist at 1? That's ET. Are we in agreement at 1? Where we're headed if we have our blinders on? Do we know for sure where we would meet? Yeah. Yes, it exists. The limit as x approaches 1 of f of x is 2. Does the limit as x approaches 1 of f of x equal the limit of f of 1? No. They're 1 and 2. And I think that's the whole point of this. Limits can exist, functions can exist, but they don't have to be the same thing. Is f continuous at 1? No. What kind of discontinuity do we have? Removable discontinuity. See, so it's just a language issue for the most part. Removable. It's tempting to say jump, But if it's just a hole, it's continuous, except that's been removed. The other ones, here's jump again, could look something like this. The other ones aren't continuous because I don't get to move on this side. So that's not just removed. I actually start again after I jump. Okay, so that would be jump discontinuity. Okay, I think this one's pretty clear. This is a circle. This guy is a circle. This guy is a circle. It really doesn't matter on the 3. We got a dot here. Find each point of discontinuity, which points are removable and not removable. You tell me as I cruise along here from -1 to 3, tell me to stop when I hit discontinuity. Yep. So let's see, discontinuity. We have discontinuity at x equals 1. What kind of discontinuity? Jump. All right, I'm going to continue from there. Stop. Right? At x equals 2. At x equals 2, what kind of discontinuity? Removable. X equals 2. Removable discontinuity. Okay? All right, number 4. Go ahead and sketch this guy. You can look up here if you have to, but try to do it in your seats. I always try to do it like, what do we really have here? Oh, I have a line with negative slope, y-intercept 3. So here's my 3 minus x, y-intercept 3, slope -1, but if I go hunting here at 2, I'm hunting with a circle. Put in 2, get out 1, circle. At 2, oh, this is in the wrong place right here, isn't it? That was bad. I'm actually down here. Sorry about that. At 2, we are up at 2. See if I can emphasize that in color. This point exists. This is bad. And then here we have a y-intercept of 0, a slope of 1/2. Okay. So continuity, 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 discontinuity. What kind? Removable. It was jump until I fixed it. So we have removable discontinuity at x equals 2. Find each point in the discontinuity. Which points are removable? Got it. Not removable. I don't list any others, so that's it. Okay. All right, example 5. There is a typo, or just I think eyes got translated when we were putting this onto when we were writing this one. Let's just make this right here be the value 3. I don't know if that's what it is. I think this is from the book. I don't know if it's 3, but it doesn't make any difference. Let's see if you can come up with a point or a location or something out of these first 2 statements. F of -2 does not exist, but f of -2 from the right, the limit of f of the limit of f of x as x approaches -2 from the right is 3. F of -2 does not exist, but its limit, f of -2's limit from the right is 3. Can you get something on your graph just from those 2 statements? Let me see hands if you know what we could put on our graph based on those two statements. F of negative 2 does not exist. But the limit of f at negative 2 from the right does exist. Jocelyn? Beautiful. Negative 2, 3 has to have a circle, correct? And extending beyond that, Jocelyn said that, yeah, from the right, we have to be going here. Now, it doesn't matter how we're getting there, so long as from the right, we're getting there. Then, says the limit at f of the limit as x approaches negative 2, period, does not exist. That means I can't be in agreement here. As I move on, I can't move on from here. I got to be somewhere else. Maybe there. This could have been an open circle. Ooh, this has to be an open circle. That was bad. This has to be an open circle, doesn't it? Because f of negative 2 doesn't exist. It has to be an open circle. That was really bad. Is that okay? So, if you understand, this open circle could be anywhere up and down here except for here. It could be anywhere, and then we move on from there. Those are definite types of problems that you would expect to see on AP Calc test from first semester material. All right, questions there? Okay, gives you about 6 minutes. You can get a head start on 2-3. Would not quiz 2-3 on Monday, but you certainly should get started on it.